Oh, that's perfect. I know how much time I have left. So yeah, I brought a core controller here, which I'm going to use for the demo, but we're going to move to it right in around like 25 minutes. I think there are several people whom I already talked with about all the ideas I'm going to present here, and I hope you all get as excited about them as I am. I work currently for the company which is called CodeCentric, and spend most of my time doing Clojure. And we have a large collection of Clojure libraries which is called ClojureVX, and most of the things which I'm going to mention today are using ClojureVX products, so it's all Clojure based. You can use this Twitter handle if you get any questions during the talk that you want to discuss and don't want to forget. Just ping me on Twitter right away. I'm going to answer to you after the talk. So this talk is rather philosophical, and it's done by the hobbyist monitoring geek in free time, so I'm not trying to compete here with anyone. It's just a tool that I consider good and stable, and it solves, well, some problem that no other tool solves, and I'm using it for myself, but I'm not trying to convince anyone else to use it. So it survived several rewrites from the scratch because, well, I didn't make any money out of it, and I'm not intending to because it's an open source tool, so I was free to just say, okay, I reached the limit of the current architecture, so I throw away entire code base and rewrite everything from scratch, and that helped me to evolve the thing. So that didn't prevent me from just saying, okay, I was just super stupid, now I'm starting all over. And I had a tons of experience. And we've got many components extracted, so it's been around 7 open source libraries that you can find on the internet. And I also need your opinion. If you have anything to say about the things I'm mentioning, please do share it. So basic idea is monitoring not about software, it's all about the insight. And current state of art is it's very easy to get started with some tool, and then you do something, some basic stuff, and eventually you want something more complicated, and it's just impossible or very complicated. And you're trying to change the tooling and it doesn't work very well, and then you say, okay, I'm just gonna jump and use another tool, but it's not that easy because you have everything instrumented and it's so complicated to change all your application code to actually do that. So the general path which everyone is following is just like, okay, I try something out, I implement more complex scenario if I succeed, and I just think, okay, I cannot go or cannot do more than a certain amount of things with my current tooling, so I'm just saying that Monitorin sucks and will try to stick to whatever I have. But I thought there was monitoring love, and we should take the monitoring hats, monitoring sucks, and monitoring hats and hat for a journey. When I hear monitoring, I'm like pony. And in my world, everyone is a pony, and they eat rainbows and poop butterflies. And I really want to redefine the monitoring toolchain, and I think we should need to simplify it. The first thing, and the foremost one, is ad hoc versus post hoc matrix. And ad hoc looks pretty much like that. So ad hoc from Latin means for this. And it means that whenever you want to, I don't know, cook a sausage, and you don't have means for that, you just use whatever there is for it. And that's pretty much what we are doing in monitoring right now. And I once wanted to understand what's going on my website, and I didn't want to use Google Analytics, well, mostly because it didn't provide enough insight, so I started doing that. Okay, my monitoring tool, increment blah, increment, I have a timer, I increment one more thing for user agent, for response type, for each response type, and then I have, well, several different meters. And then I deployed to the 100-something servers. And then I wanted to add more meters. And then I had to redeploy the entire thing to 100-something servers again. And then I wanted to, well, it kind of continued like that, and eventually, because we were a team, well, very small team, we thought, okay, it just cannot go on like that. We need something way more simpler. And we thought, why the hell, like our entire farm of servers is actually acting like a client in that particular case. So because they're sending the information to the monitoring server. Why the hell is client doing a job of server? It's wrong. So anything that a server can do, the server should do. Another example is, imagine you want a suit and you call a tailor and you tell him, okay, I'm of an average height, and here are my basic params, I'll call you later. And you expect him to start working on the suit. And then you call him, okay, the color should be gray, and hang up. And then you call him again and say, oh, my waist is like 95 or something, and hang up. And Taylor just doesn't have the complete information about you. So A, he cannot start working, probably he will refuse to even listen to you after a couple of calls. But I mean, that's how we try to work with our monitoring solutions. But why? I don't understand that. Because it's clear that a server should have a complete payload in order to help you with anything. So let's turn the ad hoc solution the other way around. We won't okay, what we're going to do, we will package everything related to the single event into the single payload. For example, when you have a page load on your website, you don't send like 5 or 10 different meters. You just say, okay, there's been a page load. The execution time took 400 milliseconds. It's been a 200 OK request, and the referrer was Google la la la, and the user agent was such and such, and there were 20 database requests made during the call. And you package it into a single payload and send it to the server, and let the server figure out how to yield metrics out of it. What it gives you granularity. Basically, you can, well, separate the events logically for yourself. You don't have to think in meters, you can think in events. It gives you a simple and stupid client, because in majority of cases, if you're not adding new things to your payload, you can change the way you aggregate the payload on the server side. You don't need to think in advance. Well, you have to kind of, but not as much, or not as deeply. And you can rethink your metrics anytime you want. And you can add more roll-ups and aggregates as you need them. So what would the monitoring system look like? I think it would look like that. It's just a bunch of Liga blocks that I can compose whatever the way I want. And that's kind of a principal schema that I considered complete for the monitoring system, and it kind of has proven itself to work. We have a reporter which uses some kind of a transport which is arbitrary. You can use, I don't know, JSON over HTTP or JSON over AMQP or whatever binary format you prefer, thrift, protocol buffers, whatever. Then the information gets to the collector. Collector pushes it to the processing unit, and processing unit dispatches it to the persistent store. I don't know, you store the data in the HDFS or Cassandra for map producing it later in case you need it. And you have a kept memory store with the latest events, because you just want to see the fancy stuff on your dashboard. And you have a little state machine that will use all that information for alerting. And you have some kind of a console that people can use for accessing, well, latest data in real time. For instance, if there's been an incident, your people can actually log into the server and query the data in real time. But since nobody got time for that, we get what we get. And unfortunately, today we don't have time for all of it either. So I'm just going to cover the processing unit, which I kind of thought is the most interesting part of it all. Let's think of a simple scenario. We have such a processing topology, I call it. And we have a splitter which gets in events and figures out whether the number is even or odd. And we push all the even numbers to one buffer and all the odd numbers to second buffer. That's kind of simple, right? It's easy to implement in whatever the programming paradigm you may think of. But let's add the counts for both. So here we get even and odd splitter dispatches the information to the two multicasts, one for even and one for odd numbers, and then multicast redispatches, well, kind of multiplexes. So it says that, okay, several downstreams should receive the same payload, and the even numbers count will aggregate, well, increment each time it gets a new number, and even number buffer will get the new number and store it together with the other even numbers. So let's now calculate sum for each 10 in addition to it all. So you get, well, pretty much the same topology, but after that you add the summarizer and the sum buffer. And the good thing about it all is you can do that. You can detach stuff, attach it back, and, well, change your topology in a real time. So whatever you see here is very composable. These are small atomic building blocks that are absolutely independent, and you use routing to define dependencies between them. So it's kind of an event-based system. You create a simple independent part, aggregates, filters, multicast, transformers, etc. You define dependencies between them, which actually means routing. If you used any queue system like AMQP, for instance, you probably know what I mean here. Parts are completely decoupled, so it's extremely easy to develop any one of them. If you develop a buffer and you make sure it works, whenever you push a number into the buffer and you check the state of the buffer, okay, it has a number, you push another number, it has two numbers, so it works. So it's decoupled, and it's going to work whenever you put it together with the other components. Every part can have its own state, for instance, buffers too, and routing is completely dynamic. And graphs or processing graphs are very expressive. So it's so easy to understand what is going on. And that is one of the examples that we actually used in production. And here you can see that, okay, we have an event of a certain type, then we extract the raw value for some metric, then, well, we split it to, well, two types of events. It could be either the window has been opened or the key has been pressed, and then we retransmit it further down the line. We get a roll-up, then we get an aggregate, and then we store it in some buffer for future visualization. But we will gonna touch the deeper example or more illustrative example a bit later. So windowed operations, that is something which is working together with the event-based system, and helps you to actually have an insight to the body of the data. Because you cannot really understand or see each one of the numbers you have in common in your system, because that just mean millions of them, and just looking at them won't give you any infos. So what you need to do is you need to use some statistics in order to determine the shape of data. So round numbers are too much. Window is an easy way to accumulate and summarize, and they're very flexible and composable. The first concept is a sliding window. It's very easy. It's basically a ring buffer. So you get a ring buffer of size 3. First you add the number 1 to it, and the buffer holds number 1. You push second number, which is 2, and buffer holds 1 and 2. You push the third number, which is 3, buffer holds 1, 2, and 3. Because the buffer is full, it makes an emit and calculates the sum of these three numbers. 1 plus 2 plus 3 is 6, and then it drops the oldest one and appends the 4, the next number which is coming to it, to the end of it, and immediately calculates the sum of the latest ones, and it's 9 now, and it drops 2 and appends 5, and we get 12. So sliding window accumulates items in a buffer. When it is full, it emits all the contents and drops the oldest value. And there is a tumbling window, which is basically looking pretty much like the previous one, but has a little bit different semantics. We have a tumbling window of size 3. We start adding numbers. We get 1, then 1 and 2, then 1 and 2 and 3. We calculate a sum of these 3 and emit it, and we flush an entire buffer, and then start appending things all over again from the beginning. So, sliding and tumbling. Tumbling accumulates items in the buffer and emits all the contents when it's full and drops all the values on the floor. And within each window, you have a clock. The good thing that clocks are arbitrary. So here we've seen that we've based our clock type of a thing on the size of the array or size of the window. So we said that you should emit whenever the size is 3, okay? But you could have said emit every minute. Or you could have said emit whenever there is a deployment occurred, because you just wanted to see all the items between 2 deployments. Or you can use arbitrary things for controlling the clock. And let's sum it all up. The basic idea is simple. So everything that is coming into your system is an event. Events are split by the triplet or identified by the triplet. It's application, environment, and event type. Well, usually that, but you can add more. Every event can have several metrics. Metrics have a key and value. Sometimes it has a filter because you don't want to get all the numbers which are identified as certain event. And it can have several rollups, which are tumbling windows, and rollup can have an aggregate function that is triggered on the buffer overflow or on emission, and sliding window with the n last values, which is basically used for visualization, and the visualization itself, area, line, or bar chart, whatever attached. And the incoming payload, the so-called post hoc payload, would look pretty much like that. So you've got an application my app, environment is production, type is page load, execution time 442 milliseconds, user agent Mozilla, host web 001, status 200. And that is an identification which gets into the splitter. And because of all the flexibility I just described, you can do pretty much following things. For instance, you can say that value is an execution time and key is a status. And what do you see here? The green line, for instance, is 200. So it's status OK. So it's basically execution time for the status OK pages. The blue line is 404s, and the red line is 304s or some other one. So you have very easy means for the configuration of it. And the aggregate is median, so you can see that, well, the graph represents the median. And here we have a value of execution time and aggregate of maximum. So we get only maximum execution time of, well, certain status code. And the orange ones, as you see here, are, for instance, 200s or 404s. So you can see instantly here that 404s are, well, slower than the rest of it. But like, I don't really care what you can see here. What I care about is how easy it is to configure. And for instance, you don't care about any thing as a value, but you only care about the key. That can allow you to, for instance, aggregate the count. Here you can see the amount of 200s, so 200 OKs are, well, above everyone, and then somewhere on the bottom you can see like 400s, 404s, 302s, and all other types of pages. So very configurable. And the key is user agent Mozilla, for instance, and well, that can give you an insight to which users were visiting or which user agents were used to visit your website. And for instance, that way you can configure that I want to see there is exceptions coming into my system and I want to spread them by the stack trace. and want to see which exceptions were occurring on my server. And all of that was configured by simply injecting an event dispatcher into your system and adding a 3-liner into your aggregate system. Now, please pardon my lisp. That is pretty much what I've been saying, just converted to Clojure. So the event is identified by the triplet, my web app, production, page load. And, well, as I was mentioning, it corresponds to whatever the part of the page load we have, or the splitter. And that's how you specify what you want to have as a grouping key and what you want to have as a value. You say, I want to have a status as a grouping key and execution time as a value. So that's pretty much what it looks like in the payload. And then you say that, okay, I want to have a roll-ups. It should roll up for every second and then aggregate maximums, minimums, and counts for everything that it gets from the buffer. And visualize it with the line graph. Now, you can say, I want to see the correlations. No problem. Box plots, you got them. Linear regression, sure, sir. Just because everything is very flexible and entirely configurable. We just give you all the primitives, and you can either use the statistical functions we have built in, or you come up with your own statistical functions. So now it's showtime. Oh shoot, I haven't thought of that type of a resolution, right? Kind of expected it to be better. So. Okay. Yeah, as I mentioned, I've brought a core controller here together with me, and I'm going to use it to, well, show you how it all works. And the basic idea, well, why I used core controller is when we started testing it all and trying to create different cases or use cases for different people, we just realized it's really hard for us to program everything for actually making a case. And then we thought, okay, how can we make it more interactive or more visual for ourselves? And we thought, okay, we're just gonna take a core controller. Here we have, well, 3 sliders. Each one represents a line. So a base number, let's say. So speed of the 200 request, speed of 302, and speed of 404. On the top here, I have a frequency, how often I want to dispatch the values, the correlation parameter, whether, well, they are, whether the items correlate or they don't. And the third is the range size. So what's the distribution of an item? And that looks pretty much like that. And as I mentioned, I just, well, have 3 sliders here. And whenever I, for instance, say that range size is really small, my box plot is, well, going to nothing, pretty much. When I say that range size is medium, for instance, oh, shoot, I'm looking at it myself and enjoying it, right? And I think, why anyone is screaming, wow, so cool. So, where is the box plot? Okay, here is the box plot. Okay, so yeah, let's see the really small box plot. So let's say that range size, the distribution of our data is really small. And you pretty much see that, well, the box plot looks ugly. Like, let's make it more realistic. Usually, we get a really large range, like from 48 to 170 something. And, well, that's controlled by that. Okay, let's just go back to the graphs, and well, we just make it all up. What is going on? So let's make a frequency. Okay, then we say that okay, 404 is going down, and now 302s are going down, and 200s are going down, and well, let's check where the frequencies are. Okay, frequencies are here, so let's make a frequency different. Okay, a little different, more different. Okay, but I mean, the thing is that I mean, it's really easy to control or program the core controller, and it's really easy to draw a fancy graph, right? But so these things don't really matter. What matters is the idea, and the basic idea is that we have to make it all simpler. And coming back to the slide with my favorite, well, sausages. I'm sorry about that. That is exactly what is important and what should matter for all of us. We just should stop making it all complicated for all of us. And what we should do is we should use a concise DSL for creating the parts of our monitoring system. And it's not complicated. I mean, that particular thing is just generating a hash. And then hash is used by the runtime to actually generate an entire graph. And it's really easy. The visual part, the graph that you've seen as a picture on the white background, it's also generated by the same software. And you can use just a JSON hash that you generate in your tool of preference, Node.js or Ruby on Rails or whatever you want, to feed the metrics into the system, and I will just recognize them and build the processing graph for you. If you're not satisfied with the way I build the processing graph and you feel it's limiting, just build your own. Because all the parts I've tried to make are very composable. I mean, I don't really care whether you run on the single box or split up to like 50 boxes, or you well, want to pipeline it all through the one machine because it's a testing environment, or I don't care. I mean, it's all so composable, and it just was built with the thought that, okay, people are going to use it like the way they want, because I cannot dictate people what they want. And it's all been built with an open source. So we are using EEP and Project Reactor, if you know that from, well, Java world, for event emitter and window operations. So it's available under ClojureVax EEP. Meltdown for anonymous topologies. Gizmo Web, that's our Clojure Web framework kind of a thing. Eventiverse graphs for, well, graphs. Pusher for WebSockets, but we have our own standalone implementation of the server that we don't push the data to the cloud. And we use Cascalog for MapReduce. And actually the same processing pipeline is entirely deployable to the Cascalog server. So we just take entirely the same configuration, and if we want to run, if we added a new metric and we want to run the query on the raw data, we can just run the Cascalog query without writing any code. We just give it a configuration. Okay, you extract the matrix that way, use certain aggregate, and you have certain rollup of the size blah. And Eventiverse is soon going to be available under ClojureVax GitHub account. And that's pretty much all, folks. And follow me on Twitter if you feel like that. And we still have 5 minutes, right? Or no? Yeah. Because I really tried to, I mean, I cut like 25 or 30 slides to just try to make some room for the questions. And there are none. Okay, no, there are.
Did you look at Riemann at all?
Yeah, sure.
Can you repeat the question?
Did you look at Riemann? Yes. Yeah, I did look at Riemann, and if you looked at Riemann, you can see that it's entirely different. actually. I mean, because this talk is recorded, I don't really want to express any opinion on anything, on any tooling. I mean, Riemann is really awesome, and I love it. It's really awesome, but it just solved a different problem for, like, whatever I was working on is solving a different problem. That's pretty much it. So it's not a replacement for Riemann. It's actually different. Okay, next time I won't cut the slides, okay.
Thanks, Alex.
Yep.